Okay. Good afternoon, everyone. You're welcome to another section of our AIPlus Club meetup. Uh, Today we'll be discussing around feature engineering. AIPlus Club is a subsidiary of Data Science Nigeria, founded by Dr. Olubayo Adekombi. And our primary goal is to gather AI talent in 1 million AI talent. And we are a group of students that actually come together to learn everything about artificial intelligence and data science. So today we'll be talking about feature engineering, how we can actually use it in our machine learning project. And this is going to be taken by Rising Odegua, who is also happens to also be a member of Data Science Nigeria. So if you're interested in joining AIPlus Club, a link will be shared at the chat room where you can send us a mail to indicate your interest, and then the response will be sent back to you. So we'll be starting the class now, and I hope you are looking forward to a very interesting and educative session. So I'll be handing over to Rising Odegua now. Rising, are you ready?
Yeah, I'm ready. Thank you very much. Yeah, so can everyone hear me clearly?
Yes, we can hear you.
I hope there's no much background noise. Okay. So, hi everyone, and I'm happy to be here with you all today to engage in this workshop and class. So I promise you're going to learn one or two things today that will help you in your next, probably your next project or anything that you're going to be doing. Okay, so it's going to be a practical session. So I'm going to quickly share. Let me share my screen, then I'll share you the link to a collab notebook, so everyone can work with me through the notebook. So I'm quickly going to share my screen now. Please, if you can see my screen, please let me know. Let me see. Okay, can you all see my notebook?
Yeah.
Okay, great. So I'm going to share the link so you can open from your end and everyone can view it. With this link. Okay. So I'm going to paste it in the chat sessions. So you all can access it. Now let me go back. All right. So welcome to the Practical Guide in Feature Engineering Masterclass. So basically what we're going to be doing here today is to learn all the underlying, not really all, but most of the important underlying techniques and tools that you need to effectively do feature engineering and extraction in Python. So I'm going to be sharing with you some tips and some tricks. There are lots of other things that you can do, but I just picked most of the important ones to share with you today. So basically, what is feature engineering? So feature engineering is one of the most important skills needed when doing data processing and when you're trying to work on a data science project. So basically what you are doing is to take, sometimes you can have domain knowledge, you can take domain knowledge and data wrangling skills to try to extract good features from your data set. Because sometimes most data that comes in the form of, for example, maybe categorical data, maybe time series data. So, and if you are going to be using this data to maybe build a model, you have to first of all process the data. You have to extract useful insights from the data. You have to maybe encode the data. So there are lots of things that you can do, and I'm going to be showing most of these things with you today. So from the definition here, it says feature engineering is one of the most important skills needed in modern data science and machine learning. It has a major influence in the performance of machine learning models and even the quality of insights derived during EDA, exploration data analysis. So what you will learn in this tutorial is what feature engineering is, which I've just explained, and how to handle missing values in your data, because most data sets during maybe recording of the data, they omit some values and the rest. So most of this data come in the form of nans, NaN in your data set. So how do you handle these missing values in categorical features, in numerical features, or in time series features? Then also we look at how to handle categorical features, because you agree with me that machine learning models can only work with numerical features. Okay, so for you to be properly modeled, you have to convert your categorical features to numerical features. And for you to convert categorical features to numerical features, there are lots of things that you need to consider. There are lots of techniques or tools that you can use as well. And also we looked at how to handle numerical and continuous features, because although machine learning models can work with numerical features, there are still some things that you can do and should do in order to properly prepare a numerical feature for modeling. So I'll share some tips with you. Then also creating polynomial features. Most of the time you might have limited features in your data set. Yeah. Oh, okay. All right. So let me increase my volume. I know we are restricted in timing, so I'm just trying to listen up. But don't worry, I'll try to be slow. So can you hear me clearly? Is it better? Okay. All right. So back here again. I said we also talked about how to create polynomial features, and most of the time your data set might be restricted, so you might have maybe just 6 or maybe 10 features, which might not be descriptive enough to build a good model. So you might want to create new features from the interactions of these existing features. That's something called polynomial features, which we also look at. Then we look at how to normalize your features, especially your numerical data, because most of the time you might have different scales, and it is better if all your features are in the same scale. So we look at some techniques for normalizing features. Then lastly, we look at working with date time features. Okay, I think that's not the last one. So working with date time features, many data sets comes with time features. You might have arrival time, maybe order time, and stuff like that. So how can you extract useful information from these time features? Then lastly, we look at working with location data or geocoordinates, latitude and longitudes. Okay, so this is just like an overview of what you're going to learn today, and so let's move on. So basically, I've explained the fitting and back feature engineering. So to do feature engineering, the data scientist combines domain knowledge. If you have knowledge about a particular field that your data is coming from, for example, if you work in a bank and the data set you're trying to work with is from the bank, so you might have domain knowledge of what the features represent than somebody that is not originally in the banking industry but is trying to work using the banking data. So the kind of insights you will get from from a domain knowledge expert is different from the one from a non-domain knowledge expert. Okay, so and it's important that you bring in this domain knowledge into your feature engineering. It's going to help you a lot. Okay, so you use this idea to transform or come up with new features that will help the machine learning model perform better. Also, this quote from Andrew Ng said, "Coming up with features is difficult, time-consuming, requires expert knowledge, and applied machine learning is basically feature engineering." I think I'm just going to zoom this in a bit. Yeah, better. Okay. So now for us to practicalize most of these things that I've introduced to you, we need data sets. So I got 2 data sets. One from a loan default prediction hosted on Zindi by Data Science Nigeria. It's a loan default problem. So if you click on the link in this notebook to take you to that page, and the second one is also hosted on Zindi. It's called the Sandy Logistic Data Set. This data set has time attributes or time features. That was why I picked it, so that I can be able to explain to you how to work with time features. Okay, and it also has latitude and longitude as well. So you can work with, you can do some feature engineering on those time features. Okay, so you can also find description of data sets in the web pages. So you can go there. I'm just going to quickly, let me see. Let me run this. Okay, I have to upload the files again. Okay. So let me quickly upload the files. These are the 4 data sets. Okay. So we have trade previous loan, trade performance, trade demographic. So this 1, 2, 3 belongs to a single data set or a data source, which is the loan default prediction. Why the Sandy logistics is for this. So meaning this loan default prediction, this guy has 3 different tables which you are going to be working with. So you have to do many things, maybe like merging the tables together, joining them, and stuff like that. And why this Sandy logistic came with just a single table. So uploaded, I'm going to now run this cell again. So what I'm basically doing is importing your normal libraries you're going to be using, pandas, numpy, c1, matplotlib, in case we want to do some plotting, ignore warnings. And I'm reading in the data sets. So you can see this first 3 is for the loan, where we have change demographics, change previous loan, change performance. I'm hearing some static noise. Hope everybody can still hear me clearly. Okay, everybody can still hear me clearly, right? Okay. So, and the second one is a Sandy logistics data set. So let's run this. Okay. Successfully imported. So let's take a look at each of them. We just maybe just take a sample of 3 from the loan demographic. Let's see what it's about. So you can see we have customer ID, birth date, the bank account type, the location of the customer, the name, the bank name, client, and the name of the bank customer is banking with, employment status of the customer, level of education of the customer. So you can see this table of loan demographics is actually information about the customer, about the person coming to take the loan. So that's why it's demographic data sets. So that's why you can see things like education, employment status, is the person employed or not, the location of the person, and the rest. Then also the date of birth of the person. So anybody coming to apply for loan, these informations are kept. Okay. Then the second one, which is trend performance. Also going to take example. These are also as a customer ID, obviously, because if you're having 3 different tables, you must have a unique key or a primary key that you can use to join these tables together. So that's why you can see we have the customer ID here, the customer ID here. So that if you are going to be joining the performance of each loan to the demographic of the customer, you can join with a unique ID. Okay. So we have this customer ID, the system loan ID. So this is the particular loan, the ID of this particular loan that this customer took. Okay. Then we have loan number. So how many loan has the person taken in the past? I think that's it. Yeah, that should be it. Then the approved dates the loan was approved, dates the loan was created, the amount of loan taken, the total due. So currently this is like the total the person is going to pay plus the interest. So the person took 10,000, for example, and now currently total due is 13,000. Okay. Then we also have 10 days, which is the total number of days given for the loan. So this is 30 days, which is like approximately 1 month. Then referred by, was it referred by anybody in the past, or was it referred by a good customer, a bad customer, something like that. So, for example, the referred by can be ID of other people in the banking database. Then this is a good bad flag, which tells you whether the loan performed good or it performed bad. So this is like what you are trying to predict if you are going to be working on these data sets. You're trying to predict if this particular loan, given all these features, approval date, loan number, loan amount, 10 days, and the rest, if this particular loan is going to be good or it's going to be a bad loan. So you can help the bank to decide, okay, if this person, for example, walks into the bank today with this information and with this past history of his loan performance, can you predict if the person will pay back a loan of 20,000, for example, in 10 days? So using this, you can build a model that can actually make that prediction. So you're using past data to train them. But that's not what we are doing here. We're just trying to see if we can prepare this data, feature engineering perform feature engineering on this data and try to see if it can work properly. So we also have the last table, which is loan previous. So this is loan performance, this is loan previous. So I think this is previous loans that each person has taken before. Yeah, that's it. So there's an unnamed column here, probably an ID. Yeah, I think it's an ID column. So customer ID as well. Remember, customer ID, customer ID, customer ID. The same primary key that you can use to join each of those tables together. Then you can notice that we have loan ID here, loan ID here, no loan ID here. So meaning this is a common key to this table, both this table. So if you are going to be joining this and this together, you can join them using the loan ID. Okay? And you have loan number, approval date, creation date, loan amount, total due, closing date, effect. So you can see this last data table has lots of date columns. 1, 2, 3, 4, 5. But 5 date columns. So if you want to work with this kind of data, you have to do some many feature extraction. Like you can extract the month, the year, and the hour, the minute, and things like that. And they might be useful when you're trying to make prediction. So data set like this has to be properly transformed, properly analyzed, and the features must be properly extracted. Okay. So you can also see there are nans, missing values in the data sets, missing values here. Which other one? So branch points, missing values, level of education, missing values. So there are lots of things that you can do. And also you can see some of the features are categorical, they are not numbers. Like bank account type, you can see savings. These are strings, these are not numbers. And you can't fit this directly into a machine learning model. You must convert them to numerical form, which I'm going to show you shortly. Then you also have location, latitude and longitude. Then you also have numerical features like loan amount, total due, 10 days, and stuff like that. This is for the first data set. So it comprises of 3 different tables. And for the second one is a logistic data set. So from the data description in the page, on Zindi, the problem you are trying to work on with this data set is to predict time of arrival of a dispatch rider. So it's a logistic company. So what they are trying to do is that given a particular order to a particular rider, how long will it take the rider to get to that location? So that is like the time from pickup to arrival, the estimated time from pickup to arrival. So this can actually help the logistic company better plan. So for example, if this user, for example, makes an order, which is this order. So if I give it to a particular rider, I think there's another data set. There's another data set that contains the rider information that I did not import. Okay, but we can leave that. But there's another data set, just so you know, that contains rider information. So as I was saying, given this user making this order and passing this order to this rider, how long will it take the rider to get to the location? So that is what you are trying to predict. So you are given lots of features like the vehicle type, platform type, business or personal accounts, placement day, the day of the month it was placed, the placement time, the confirmation time when it was confirmed. So for example, I placed the order at this time and the order was confirmed by the company or by the rider at so time. And pickup time, what time did the rider came to pick up after confirming. So you can see these are all things that can greatly help in predicting the time of arrival. But the same, we're not going to be modeling, just going to give you an overview of data sets. So you can see that we have lots of time features as well, lots of numerical features, lots of categorical features, which we are going to be processing. Okay, so now that we have an understanding of the data set, now let's dive into the next step of this tutorial. I hope everyone is following along. Okay, so the first part is how to handle missing values. Okay, so we saw in data set that there are lots of missing values, nans and the rest. So how do we handle those missing values? Now, for you to handle missing values, it's going to depend on the type of feature that you want to fill with missing. You want to fill. So if you have, say, categorical features, there are different strategies that you're going to be using to fill missing values. And if you have a numerical feature, there's also a different strategy that you can use to fill them. Okay, so the choice of handling missing value is dependent on the type of feature. So for categorical feature, you can do things like, so these are types of or ways that you can fill a categorical features. Please note that categorical features are features that come in the form of strings. Okay, so you can maybe have like level of education, which can be tertiary, secondary, primary, and the rest. Or you can have say type of food, which could be sorry, types of food. Forgot the types of food, but you get the gist, right? So those are categorical features. So now, for you to fit categorical features, you can do things like mode filling. Now, what is mode filling? Mode is simply the most popular or the most frequent class in a feature. So if, for example, I have a feature of types of food, and I have rice occurring like 8% of the time, if I have missing values in that feature, the best bet is that these missing values are also going to be rice, because I have lots of uh, examples or lots of instances of rice in my data set. Okay, so that's the essence of mode filling. So you are trying to fill missing values with the most popular or frequent, sorry, that most popular or frequent uh, class, right? So that's mode filling. I'm going to show you shortly. Then the next type of filling that you can do for categorical features are temporal filling. Temporal filling are also called forward or backward fill. That means you fill the missing values based on the preceding values or based on the succeeding values. What do I mean? So if, for example, I have a column that has, let me just quickly wait. So just create something like this. So I have a column that has 1, say 2, 3, and I have 9, and I have 4, and I have 5, for example. So for me to do temporal filling for this kind of feature, for example, what I can do is I can use what is called forward fill, whereby I will take the last, the preceding value and use it to fill this. So meaning the preceding value to 9 here is 3. So I'll fill here with 3. That's what is called forward filling. So I'm doing temporal filling in respect to time. Okay. But if, for example, I was using the second method, which is backward filling, I'm going to fill with succeeding values, which is what 4 actually. So here will be 4. So this type of filling is mostly done in for features that have kind of temporal ordering. That means they work with respect to time. Okay. So it's mostly used for this kind of categorical features. And the other type of filling that you can do is encoding and filling. This is kind of like an experimental method. I've not seen it used a lot, but you can actually try it. So what you can do is to first of all encode the categorical features. Encoding can be from maybe label encoding. As the encode simply means converting them to numbers. So after converting the categorical features to numbers, you can now maybe do fill with maybe the mean, calculate the mean, fill with the mean, or you fill with the mode, or you fill with the median. So this guy's called encoding and filling. Okay. So an example, I'm just trying to show you some of this example practically. So I'm using the known demographic data set. So remember, let's check which of them have missing values. So to check, you can use known demographic is NA sub. So this is going to return all the features, all the number of missing values in each of the features. So you can see this feature, bank branch clients, has 4,295 missing values out of 4,346. So this one has mostly missing values. And employment status has 648 missing. Then level of education has 3,759 missing as well. Okay. So let's see. I think this employment status is a categorical feature. So let's see how we can do that. So to fill with mode, the first thing to do is to get the modal class of that particular feature. So we take this feature and we do a value count. So value count basically it tells you all the number of times each of the class appears in the feature. Okay. So for permanent, which is like an employment status, person is permanently employed, it appeared 3,146 times. Then for self-employed, just 348. Students, 142. Unemployed, 57. Retired, 4. And contract, 1. So for you to fill with modal value, you can see that permanent is the most popular class. Out of 4,346 data points, it appeared 3,146 times. That's about, I think, close to 80-something% of the time, even more than. So if I want to fill with the modal class, I'm going to fill with permanent. So I'm going to replace every none in this feature with permanent, because I'm assuming that if these guys are missing, they are most likely going to be in the permanent class. Okay, so that's what I did here. So what you can do, you can use this efficient function in pandas, fill NA, which is fill missing values. And so for this loan demographic employment status, fill NA with value equals to what? Permanent, which is the modal class. So if you check now, you can see it is filled for permanent. So that's for filling with modal. Then for the temporal, I've already explained, so you can easily do that. Just get the succeeding values. Yeah, I think there's a backward fill. For fill NA, there's a feature called B fill, I think it's fill NA. Yeah, I think I've forgotten the function. But you can actually specify if you want to do forward fill and backward fill with that. And encoding as well, you can also try that. Okay, so let's move to numerical features. Yeah, so for numerical features, there are popular things that you can do. So most of the time, both fill the main of the feature, both fill the mode also, and both can fill the median. So it depends on the particular data set, depends on the feature. So most of the time, if your data is it's normalized or kind of uniformly distributed, it is efficient to fill with probably the mean of the data. Then if your data is skewed maybe to the left or to the right, it is advisable to maybe fill with the mode or the median. So most of the things are kind of like trial and error. You can actually try to fill with the mean, maybe train a model and see if it responds better, then maybe try and fill with the mode and things like that. Okay, but by intuition, you can use a mean when your data is like uniformly distributed. Okay, so you can also do temporal filling for numerical features as well, and you can use machine learning models to learn the appropriate fill value. So this is kind of like a kind of efficient method as well, whereby you treat your meeting values as a prediction task, whereby you train a model to try to predict this particular feature. So I'm going to show you how to do that. So for this, I'm going to use the sandy logistic data. So I'm going to check for the missing value of the data. So you can see, yeah, we have temperature and precipitation in millimeters having lots of missing values. Okay, so I think, yeah, temperature is a numerical feature, yeah, because it's measured in degrees centigrade. So let's see how we can fill it using any of those methods. So to fill that, you can see I calculate the mean. So in pandas, you can just specify, choose the feature, and you can just call any of these central tendency function, which can be mean. So I just call dot mean. It's going to calculate mean of this, return a single number, which I'm going to round up and save in this variable. Also, you can calculate the mode. Now, most of the time, the mode is going to be coming as a list. Why? Because you can have more than one mode in a data set. If I have two values occurring the same number of times, so I'm going to be having two modes. So you can decide to choose the first one, which I did here by specifying 0, or choose the second one. So it depends, it's up to you. And you can also calculate the median as well. So to fill with the mean, it's simple. You can also use this function, very efficient function, fill NA, passing the value, which is the mean I've calculated, and to automatically fill all the missing features in temperature. Okay, do the same thing for mode as well, and do the same thing for median. So you can see, I just printed the values I used to fill the temperature. So you can even see that they are close to each other. Mean, the median, and the mode, they are kind of close to each other. So that's for filling with mean, mode, and median. Then I think, okay, these are just like some basic simple explanation. Yes. So we can also do filling with machine learning models. So this I'm just going to show you quickly. Now, how do you do that? It's very simple. What you can do is that take the feature that has missing values. So in our case, we've already fit temperature. So let's take the second one, which is precipitation in millimeters. This is also a numerical feature. So let's try to use a machine learning model to fill missing values in this particular data. So the first thing you need to do if you want to fill with modeling approach is that you can decide to write your own simple linear regression or a very simple model that can do that for you, or you can decide to use, there's a tool called iterative imputer, iterative imputer in sklearn that does the same thing that we're trying to do here manually. It does it for you. So you just need to just pass in the features that you want to use, fit transform like you're training a model, and to do the filling for you. Okay, but I'm just going to quickly show you how you can do it by yourself. So the first thing to do is to get correlated features to the one you are trying to fill. So in our case, we are trying to fill precipitation in millimeters. So we want to look at the data set and pick features that will feel are highly correlated to it. Because if we can get features that are highly correlated to it, we can use those features as inputs to learn how to fill missing values in these particular features. Okay. So what we can do is to use this the heat map function. First of all, we calculate the correlation matrix from the data set, which is the data set this.core. So we pass in that correlation matrix to the heat map for seaborn. It's going to make a plot like this. So let me just zoom out a bit. So you can see this is the plot, and the feature we are concerned about is this precipitation in millimeters. And you can see they are mostly dark, and that tells you that most of the features are not correlated to this guy. Okay, so but we just have some few ones at the end in here. I think these three also that are a little bit correlated. So we can decide to use these features. Okay, so which features are they? They are time from pickup to arrival, which is actually the target, destination longitude, and destination latitude. Okay, so these three features are a little bit correlated to precipitation in millimeters. So we can decide to pick these features and use it to predict the missing values in this particular feature of interest. Okay, so how do we do that? You can use, so it's advisable to use a very simple model. Very simple model, so you don't run the risk of overfitting, because it's a very simple feature, just three features. So you can use a basic linear regression or something very simple, or a decision tree. So I'm using a linear regression here, which I imported from sklearn, the linear model. So these are the features that I want to use. So you can see this is what I'm trying to predict. So I'm treating this as like a mini machine learning project, whereby I have these features and this is like my target. So I want to use these features to predict this guy, predict the missing values in this guy. Okay, so meaning I'm going to like create a small data set from this, whereby all the available points in this guy will be my training set, and the missing values will be my test set. So meaning I'm going to train on the existing values and going to learn how to predict on the missing values. So that's what I'm doing here. So basically, you can just drop all the null columns and save them in the training. So meaning all the ones that are not missing, add them to the training data. Then get the precision in millimeter as well. Then for the test set, all the ones that are missing, send them to the test set. So I'm going to train on these two, this and this, as these two. Can't copy that. Okay, I'm going to train on this and this. I'm going to use that knowledge or that model to predict on this. Okay, so just see a simple fit and we train on the test. Then I make a prediction on the test set. So I take those values that the model predicted as my feed values, and I'm going to run them up, and I'm going to replace them. So anywhere that I have is null, I'm going to replace them with those particular features. So you can see these are the features that it's predicted that we should use to replace the missing values. It's a very very simple way you can do that. But if you don't want to go through the stress of this, you can actually use the iterative imputer, which automatically does that for you. So what do? You can import it first. So what you have to enable it, because it's like an experimental feature. It's kind of new, but I don't know if it's stable now. Kind of new in sklearn. So you can first of all enable it, then import it. So it follows the same method. So I'm just basically using a random forest here, which is not advisable because it's a very small, prediction problem. So you can use something simpler. So you pass in the random forest model. So this is the random forest model. Okay. So normally define your random forest model, passing an estimator. Okay, then the number of times you want to iterate, you want to go around, then random state and the rest. into the iterative imputer object. Okay, so then select the features. These are the same features that we want to train. Now this time, since we've already done from precipitation in millimeters, I just decided to try it with temperature as well. Okay, so normally we've already filled temperature here, but you can just maybe rerun the data set from the top and just try this. Okay, so now, so you do a fit transform. Remember, if you're working with sklearn, it uses the same API, which is fit, transform, stuff like that. So we call this object we have created fit transform. Will pass in the training data sets, okay, which is this, and this, and call them columns to train. Then when we are done, which is, so remember we're doing fit transform, so meaning it's going to fit and it's going to maybe transform it as well. So it's going to fill in missing values in that particular data set. So it's a simple method. You can actually decide to use this, or you can decide to just create something simple like this. So those are like some technical ways that you can fill missing values in numerical features. Okay, then the next step is how to handle categorical features. Okay, so I think probably I should look at the chat sessions. If link to notebook, just joining. Okay, somebody has sent that already. All right, so let me just maybe I'll take questions at the end of the class so that we will not waste too much time. So to handle categorical features, most of the categorical features come in the form of strings, which we said earlier before. So, and your machine learning models can only work with numerical features. So you have to look for a way. There are lots of methods that you can use to take these categorical features and convert them to numerical features. So they are practically called encoding. Okay, so and there are different types of encoding schemes. But the idea is that before you can encode a particular categorical feature, you have to understand what type of categorical feature it is. Okay, so because we have basically two types of categorical features, which are ordinal categorical features and non-ordinal categorical features, which is what I have here. Yeah. Okay, so ordinal means there's an ordered category, meaning there's ordinality. That means a particular class can be higher than another class. So, for example, I give an example with star ratings. So I can have different star ratings, which is like 1, 2, 3, 4, 5. And also, I think I should mention something that when I mean categorical features, it doesn't necessarily mean it must be strings. Sometimes you can have numbers that represent categories. Like, for example, this is star ratings. You have just 5 star ratings, 5 discrete star ratings. So it's not a continuous feature. It's not continuous in the sense that you don't have 1.5 star, you don't have 2.5 star, and maybe 6.5 star, something like that. You just have maybe 1 star, 2 star, 3 star, 4 star, 5 star. I hope I'm right. But so this is a categorical feature, even though it is in numerical format. Okay, so this is like an ordinal categorical feature. Why? Because a particular class is higher than the previous class. So for example, 5, if I give a 5-star rating, is higher than when I give a 4-star rating. So there's an ordinality in this feature. So if I am going to encode this particular feature, I have to take into consideration the ordinality in it so that I can efficiently utilize this particular feature. Okay. Then the next type of categorical feature is non-ordinal categorical features. So these features have no order. So there is no class that is greater than another class. So an example could be maybe food. I love food, maybe because I've not eaten this morning. Okay. So an example could be food. So if you can't say that rice is higher than beans or beans is higher than bread. I know, practically you can't say that, but some people might say, yeah, I think there are some food that are higher than others, but let's neglect all the sentiments and the rest. You can't say that a particular food has an higher ordering than another food. Okay, so in that kind of feature, there is no ordinality. So you can consider encoding schemes that work well with these kind of features or categorical features. Okay, so now that we know the types of categorical features that we have, what kind of encoding can we use? Okay, so let's say, for example, for ordinal features which have ordinality, like we said, you can use a form of manual encoding. Manual encoding in the sense that you take into consideration the the ordinality of those features. So for example, in this data set, so we have loan demography, or we have level of education. You can see that we have non missing, secondary, graduate, postgraduate, and primary. So looking at this feature, you can easily tell that this is an ordinal categorical feature. Why? Because you agree with me that postgraduate is actually the highest level of education in this particular feature, followed by graduate, followed by secondary, followed by primary. So there's a kind of ordinality in the sense that a person that is a postgraduate has a higher level of education than somebody that is in primary. And there are some kind of things that this person might do that this person will not do. So you must take into consideration this ordinality when you are trying to encode this particular feature. So a quick way, a simple method I can use to quickly encode this is to just assign them integers manually. So I quickly create a map that map each level of education to an integer. So I gave primary 1, secondary 2, graduate 3, and postgraduate 4. So you can see I take into consideration the ordinality of this particular feature. So this, what I just did, is called label encoding, whereby I take an integer and I map it to a particular class. This is label encoding, but I'm doing it manually. Why? Because I have just 4 classes. But if there are some features that might have over 100 classes or 50 classes, you don't need to do this manually. You can use the label encoder function to quickly do that for you. Okay. So what I'm doing here is label encoding manually. So to do that, I just simply take the data set and the feature and just map it to this dictionary I have created. So to automatically assign anywhere it says primary, to change that to 1, anywhere it says secondary, change that to 2, like that. So if I do a value count, you can now see that's automatically converted them to numbers. And you can see this class 3, which is let's see, graduates is the most popular class, 420. That's label encoding, manual label encoding, because I'm doing it by myself. Okay. So you can also do automated encoding, and there's an efficient library which I like to use for that. Although there is label encoding and one-hot encoding in sklearn, which is popular, but this library is very efficient, called category encoders. It has lots of numerous encoding schemes out of the box, and it supports pandas data frame, which you mostly be working with. Okay, so you can just quickly install it using pip install categorical encoders, category encoders. So you can use label encoding there. There's ordinal encoding. There are lots of encoding that you can use there. So since I'm on rollout, okay, there's no need to run that thing. It's already here. All right. So label encoding is useful when you have large number of classes. Remember, in the previous one, we did it manually because we have just 4 classes. But if you have a categorical feature with large number of classes, you can use label encoding function in sklearn in the category encoders. Okay. So let's look at all the categorical features and see which one has lots of classes. So to do that, we just simply loop over all the categorical features in loan demography dataset and print the number of unique classes. So this n unique, there's unique and there's n unique. N unique means number of unique classes. So you can print the number of unique classes in this particular feature. Okay. So to do that, you can see customer ID 4,334. That's very large, but it's an ID column, so which is kind of like useless to us if we're going to be modeling. Okay, so we'll not consider that. We also have bets. Yeah, bets is time based, so there are lots of different bet dates, but it's not a categorical feature. It's a time feature, date time feature. So we consider that. We will not consider that. So this one has just 3 classes, small. This one has 18 classes. Okay. Then this one has 45 classes. Okay. So we can consider this and this to automatically label encode. So bank branch client is simply the names of banks, and there's no ordinality in that. So you can't say First Bank is higher than Union Bank and stuff like that. So meaning we can label encode this guy. And we also have bank branch client. Okay, this is bank name client, bank branch client, the same thing. There's no ordinality there. Okay, so to use label encoder, we just simply import it after installing it. Then we specify the columns that we want to label encode, which is these two. Since they have high number of classes, we want to label encode them. Then we just simply call the function ordinary encoder. So ordinary encoder is simply as label encoder in categorical encoder. So we create the object, passing the columns that we want to encode. Then we call the fit transform. So one thing that categorical encoder, one thing I like about it is that they also use a similar syntax as sklearn. So you can call fit, you can call transform, and stuff like that. So you just call fit transform, pass in the data. So you pass in the old data frame, and it's going to pick just this specified column, and it's going to label encode all the features, all the classes in a particular feature. So that's label encoding. So once you are done, let's see. What do you encode? Bank name clients and bank branch clients. So if you look at bank name client, you can see 1, 2, 3, 1, 1, 1, 1, 1, and stuff like that. So it has label encoded then automatically. So that's what that's. Then if we have let me say low number of classes, for example, and there is really no ordinality in data sets. So for example, in this particular one where we have, say, three classes, bank account type, 3 classes. In such case, we can use one-hot encoding. Okay, so label encoding is efficient when you have many classes, just like you have 45, 50, and the rest. But since we have just 3 classes, we can use one-hot encoding. Okay, so the one-hot encoding uses binary values to represent classes. So it creates a feature per category. So meaning if we're going to be using it for this particular feature that has 3 classes, it's going to create 3 extra columns to add to our data set. So that is one of the disadvantages of one-hot encoding, is that it enlarges, or it makes your data set bigger after you encode a particular feature. So imagine you try to use one-hot encoding for this feature that has 5 classes. It means it's going to create extra 55 columns to add to your data set. So that's why it's advisable to only use one-hot encoding when you have a small number of classes. Okay. Right. So let's see, bank account type and level of education, which we have just 4. Here we have just 4 classes, and here we have just 3 classes. So to use that same thing from categorical encoders, you import one-hot encoder, pass in the categories that you want to encode, and you also do your fit transform by passing in the data sets. So you can see this library makes things efficient for you. Because if you're trying to use maybe sklearn, you have to pass this there and maybe convert it back to the data frame, stuff like that. But this one works seamlessly with data frames. Okay, so we'll quickly move to the next one. This is just trying to display what we've done. And there's also another scheme called hash encoding. So there are lots of schemes, but I'm just highlighting the popular and important ones. So hash encoding or feature hashing is fast and efficient way of encoding features. So it is very efficient for categorical features with large number of classes. So one disadvantage about label encoding is that if you use label encoding for features that do not have ordinality, number one, and have large number of classes, it can trick your machine learning model. Because if your machine learning model sees a class that say that there's no ordinality, but for example, I assign say 20 to the food class, to the rice class, and I assign say 15 to the bread class. If I use that to train a model, it might deceive a model in the sense that the model might think that the rice class is higher than the bread class. Why? Because it's seeing that I assigned a higher number to rice. So sometimes we might not want that. Okay, but we don't have any option because label encoding is automated and fast. So, but we have this hash encoder that you can use in situations like that. So hash encoding is very efficient for category features with a large number of classes. It works by applying a hash function to each feature. So each feature has a unique hash function. Okay, that's each class has a unique hash function. So and it's very easy to implement. For you to implement that, you just simply use the categorical encoder as well, and you can just call it, create an object from it, then call the function, pass in the categorical features, and also there's something you can also pass in called the number of components. The number of components is like a dimension, like a vector dimension that tells you how large you want the function to be. Okay, so most of the time, the larger the components, the more efficient it might be, but it has like a limiting point. So you can play around with like maybe 5, 6 to maybe 10. So you can see this is the hash, this is the columns. I think I should, no, if I run that, I have to go back to the top. So I'm not going to run that. But what I just simply did is I transposed this feature. And so you can see these are the columns that is going to add to your data sets. So to specify 10, it's going to add 10 features to the data set. So if you don't want something very large, you can decide to use maybe 5 also. All right, so let's move to the next one. Also, there's also another one called target encoding. This one is in target encoding, we place a categorical value with the mean of the target variable. So it has some little bit of mathematics behind it, but you don't have to maybe understand those maths behind it. You can just simply use it by calling it from the C library as well. Okay, so most of the importance of this is that it kind of encodes the property of the target class in your feature. But most of the time, it's my cost overfitting your machine learning model. I've noticed that most of the time, if I use it, it kind of causes overfitting. So you can try that as well. So remember, the same way you use the other ones, that's how you also do that. All right, so let's move on to the next part, which is how to handle numerical features. So we've done how to handle categorical features by encoding them and converting them to numerical features. So the next part, which I'm going to run through, is how to handle numerical or continuous features. So numerical features are the most common type of features found in data sets. So they can take different type of range, can be between 1 and 1 million. It can be between 0 to 1, whereby you have 0.2, 0.3, and stuff like that. And so there are lots of things that you can actually do, because most of the features can be skewed, can be left or right skewed, can be non-uniformly distributed, things like that. Okay. So one thing that you can do this kind of features is to do a log transform. Okay, because most of the time your most machine learning models make a simple assumption. They make a simple assumption that your data or the feature is uniformly distributed. Okay, so they just assume that the data is perfect, it's balanced. Okay, and most of the time it's not so. So most data come in different formats. Some are skewed to the left, skewed to the right. Like take, for example, look at this data set, it's right skewed. Okay, so you can see it's not centered, it's bent to one side. So in this kind of situation, if you feed this kind of feature to a model, it's most of the time it might not have an effect on the performance of the model, but in some models, if you try to uniform this feature, it can help your model actually do better. So what can you do to make this better? You can pass it through in this case, it's very simple. You just can use NumPy to do that. So you just call the numpy.log1p, pass in the feature that you want to log transform. So you can see it has log transformed it, and it is kind of distributed around the center. It's not kind of normally distributed. So this kind of features are better to work with. Machine learning models prefer this kind of feature because this is the kind of assumption they make on the data. So if they see that the data is coming in this format of the assumption they make, it might help them do better. So notice that I'm always using might, because most of the things that we do in data science projects are kind of experimental, try and error. You might decide to try this today and it works well, and tomorrow it does not work for a particular new data set. So that's why we do a lot of prototyping and experimentation. So you can try this in your projects. So we'll quickly move to, yes, this is a small section that says using of domain knowledge. So I talked about domain experts before when I started. They are very important when you are doing feature engineering, because if you have an understanding of the data set, you can actually create more features from it. You can know how to manipulate the features. So that is why if you are working on a project related to a particular industry, it is better if you engage people that are working in the industry, so you can maybe pick their brains and try to get an understanding of the interaction between features in your data set. So if, for example, you are working with medical data, you can reach out to a doctor then the doctor can maybe help you better understand your features, or what kind of features you can create, or what kind of strategy you can use to fill missing values and stuff like that. So domain knowledge is important. So I'm just going to quickly show you an example of using domain knowledge in the bank, in the loan data set. So there's something called interest on loans. So you can have the loan amount and you can have the due, total due, which is like the interest plus the original loan amount. So if I took a loan of 10,000 and after 30 days, I now have say 15,000. The interest is going to be calculated based on total due minus the loan amount I collected. Okay. So what am I doing? I'm using just basic principles of economics. I think that's economics. I'm using just that basic knowledge of how to calculate interest to kind of get this new feature, which might be important. So this feature, interest elapsed, might be important to our model. Okay, so there are lots of other things that you can do, like you can calculate the rate. So if you did simple interest, you can know that you have the principal, you have the time is in the data set, that's the duration, you have the interest now, so you can kind of calculate the rate. So these kind of features that you calculate can actually help your model do better, because the more rich your features are, the more better your model can perform. So you can see this is an example of using domain knowledge. Okay. Also loan counts as well. So you can maybe calculate the total number of loans collected by a customer by aggregating all the loan numbers. So for example, if a customer has collected 20 loans in the past, and out of these 20 loans, he has not defaulted in any of them, that can be an important feature in predicting if that same customer will default if they give him a new loan. So you can see these are important things that you can get from your data set. So you can also do that using a group by function, customer ID, take account of the loan numbers. So that's what I did here. So you can see loan number count. This particular person has taken 11, 11, 11. This is 6. Okay. So also another one is speed. So we're using the knowledge of physics. So in the data set, in the semi-basic data set, we have the time of arrival and we have distance. We have the time and we have distance. You can calculate the speed of the dispatch rider, and the speed can actually help predicting time of arrival, because if we know the rate at which the driver is going, we can kind of predict when the driver will get to a particular location. So you can calculate speed from by just saying distance divided by time. So I'm using the knowledge of physics, the length in secondary school, to kind of get this new feature. So you can see here, I'm using domain knowledge. So there are lots of other things that you can do. So if for example, you engage somebody that works, a physician, for example, and show them these features, they can kind of like advise you, explain what you need and you should do. It can help you create new and better features. Okay, so that's the use of domain knowledge. So we quickly move. I think more than 1 hour. So in the next 30 minutes, you should be done. So I'm just going to go to the other ones. So the next one is preliminary features. So remember I said that sometimes you might have a little number of features in data sets, and it might not be able to capture what you're trying to do. So if, for example, I have say 10 features, it might not be able to properly model the problem I'm trying to solve. So you can kind of create new features or kind of cross these features together to come up with new and better features. So under the hood, if you've worked with neural network, under the hood, neural networks kind of do this kind of feature extraction for you, whereby it correlates different features together. So preliminary features are creation of interaction among features. So it helps to capture relationships among independent features or variables and can help decrease bias of machine learning model by not contributing to massive overfitting. Okay, when it is not contributing to massive overfitting, because most of the time it can lead to massive overfitting of the data set of your model. So try it with caution as well. So it's very easy to use. It's already implemented in sklearn. So you can just do from sklearn the processing, import polynomial features, create an object, remember the same API fit transform. Then which features do you want to cross? So for example, in my loan data set, I want to cross the loan number, total due, and the 10 days. I want to cross them together. Cross simply means maybe I'm adding 2 of them together, or I'm multiplying them together, or I'm dividing them. So that's like I'm just applying different mathematical operations to them to kind of cross them together and create an interaction among these features. So you just call the polynomial poly.fit transform, pass in the data set or the columns dot values, and to create a cross feature for you. So you can now add this feature that has created back to your original data frame. So if you print that, so let's go to the, I think, what did I print? Yeah. Okay, so these are 1, 2, 3 to 9. So why? Because I have 1, 2, 3 features. So 3 by 3. So you're going to cross the 3 of them together and you're going to create new 9 features for you. So you can see these are the results of the cross. So you might so you can see that helps to add extra features to our data set, which can help the model if it is not contributing to overfitting. So you can try this as well. So that's for numerical features. Then the next session is on normalization of features. Now, you might ask, why do we normalize features? First of all, let me explain what normalization is. So normalization is simply changing the values of numerical feature to a common scale. Scale in the sense that you might have, for example, loan amounts that is in your thousands, can be 10,000, 20,000, 50,000, and so on. And you might have, let's say, what can I use? Okay, let's say 10 days, which can be in your 30s, because can be say 30, you can have like maybe 30 days, 20 days, 25 days. So you can see these two features, their scales are massively different. Okay, so while one is in the 1,000 scale, another one is in the 100 scale. You can also have another one that is in the maybe 10 scales, so can be between 0 and 9. So these scales are massively different, and if you are training a model with these kind of features, it's like giving the model more work to do, because it's trying to look for the correlation between features at different scales. Okay, so especially for neural networks, it's in fact, you must standardize or normalize your data before you can train a neural network properly. It's like it's a must. You must do that. So, but for some models like the tree models, they don't really consider scales like that. But it's also important to help faster training. Okay, so it's good to normalize the features, and there are different methods that you can use to do that, all implemented in sklearn. So there's standard scalar, there's robust scalar, there's min-max scalar. These are all like different variants. So anyone choose to almost the same thing. So standard scalar removes the mean and scale to unit variance. Robust scalar using statistics that are robust to outliers. So if you have outliers in your data sets, so you can decide to use this robust scalar because it's scalable to outliers. And min-max scalar, you can start to choose a range that you want. So for example, if you want all your features to be between say 1 and 10, you can choose that when using the min-max scalar. So I'm just going to quickly show you how to use some of them. So standard scalar, so for example, loan amount, total due, 10 days, just going to create an object from it, same API, and fits transform on that as well. So it's going to, so you can see they're all scaled now. So it's going to remove the main scale to unit variance. Robust scalar, the same API. So you just create an object, fits transform on the features that you want. So you can see these are all easy to use. Min-max scalar, same API, same method. You can do that. So okay, so you can see I specified the range here as well. So which one is that of min-max scalar. All right, so now let's quickly move on to the next section, which is working with datetime features. Now, datetime features are very, very popular. And as you can see in the data set that we have, there are over 6 features, even more than 6, that are actually datetime features. So, and the good thing is that pandas support datetime features effectively. So once you can convert a feature or a row to datetime pandas format, you can easily work with it. So it's very, very efficient. Okay, so what can you do with datetime features? You can do things like extracting the date components like day of the week, day of the year, hour, minute, seconds, quarter, day of the month, and stuff like that. So why is this important? So assuming in the case of our single logistic data, where you have a dispatch rider, if you know the hour of the day that the dispatch rider took on the journey, you can easily, like using domain and no, like using your knowledge of the place, you can easily tell if the person is going to arrive on time or not. So assuming you are in Lagos here and you dispatch a rider around say 5 close of business time, you'll be certain that that driver will not get to the location on time. Why? Because there are lots of traffic around that period. So just knowing the hour of the day, you can kind of like predict time of arrival. So you can see that these are important things that you need to do to your time features. So you can extract those features. What is the day? What is the week? Is it on a Sunday? Is it on a Sunday? Maybe the roads might be clearer, so the driver might get there on time, stuff like that. You can extract dates. You can also extract time-based features like evenings. Is it in the evening? Is it noon? Is it night time? Things like that. You can also extract seasonal features. Is it a rainy season? Is it a dry season? Is it Harmattan period? Things like that. So you can extract these from date features, and they can help you in making predictions. You can also extract specific features like national holidays, religious break, is it a festive period, things like that. And you can also calculate time elapsed between two date features. So what is the difference between arrival time and, say, for example, origin time? Okay. So to do this, they're very easy to do. So the first thing that you should do is to convert the particular feature that you want to work with to pandas date time. And to do that, you just call pd.toDateTime. And this one was when the loan was created. Okay, so first thing is to calculate time elapsed. So time elapsed is like the difference between two date time. So what is how many days or how many seconds it was there between the creation date of the loan and when it was approved? Okay, so to do that, you just simply subtract the approved date, the creation date from the approved date. Now you can only subtract because you have converted to date time. Normally, if you're going to subtract on its own like this, it will show an error because that's Python cannot subtract from string features. Okay, so make sure you convert to date time before you can use the subtract function. So once you subtract creation date from approved date, this is just simply converting it to seconds. So you can do minutes, you can do hour and days. So the date time elapsed in seconds. So if you do that, you can see. So for this particular dispatch, this particular loan, the difference between the creation date of the loan and when it was approved is 3,609 seconds. So you can be surprised that this feature might be important in predicting loan performance. So that's for that. And we can also extract date features like day of the week, which I've seen before. So to do that, you just simply first of all convert to date time, like we said. Then after converting to date time, you can access the date time properties by pandas. So to do that, you just do .dt, then what you want to access. So it can be day, it can be week, it can be hour. So there are other things that you can also extract as well. So excuse me. So I put a link there that you can use to see other features that you can extract, like is it the end of the month? Is it the beginning of the month? Is it the middle of the year? So things like that. All right. So we also say we can get period of the day. So we can map each hour of the day to a particular time. So you can see between the hours of 0 to 12 is somewhere in the morning. Then between 13 to 16, somewhere around afternoon, and the rest is evening. So we can use this. So whereby we take the hour, which is what we have here, the hour, and map it to these specific categories. So if you look at this now, you now have, so this particular loan was dispersed in the morning, this was in the evening, this was in the afternoon, so things like that. So that might also help your model. So there are also many things that you can do with the time series. There are lots of things. Most of the time, these features, these things that you'll be doing, you might not want to be writing long lines of code to do this over and over again. So I implemented most of these things in my in this open source library data system. So there's a time series module. So you can easily do most of these things with just a single line of code. So you just call extract it, and it automatically extracts everything that you need. So you can check it out. The link is also there as well. Okay. So the last part here, I think this is the last part. Let me confirm. Yeah, this is the last part. So we're almost done. The last part is working with latitudes and longitudes. And there are lots of things that you can also do with latitude and longitude. Like, for example, you can get the location of the place from just the latitude and longitude. So if, for example, I stay at latitude 6 point something degree and longitude 5 point something degree, with just that thing, there are numerous services that you can use to convert those latitudes into an actual name or an actual address. So, for example, if I use the Google, I think what's the name of it? Like the what's the name? What's the name? But there are lots of libraries that you can use. There's GeoPy, there's GeoJSON. So you can pass this latitude and longitude and numbers, and they will return the name of the place. So it can be say 12 Yaba Road, Lagos, something like that. So from that name of the place, you can actually get other features like what is the state, what is the city name, what are the closest, so is it a city, is it a town, is it a village, so things like that. But if you have, say, 50,000 rows of longitude and latitude, and you want to use these services to convert those numbers into words, it's going to take the time, number one. It can be running for days. It's going to cost you a lot because most of these services, they give you a limit. So maybe when you have maybe after converting like 1,000 requests per day, you have to pay for the rest. So these are all things that you can consider. Maybe when you have time constraints and money constraints, you might not want to go that route of converting your latitude and longitude to string first before you do feature engineering. So these methods I'm going to show you here are easy methods that you can use to extract information from your latitude and longitude without converting them to string. Okay, so it is based on a technique from this amazing kernel on Kaggle that the link is also there, you can go through it. So I'm just going to summarize some of the techniques that he explained there that are very, very efficient. Okay, and it's also important to know that these techniques have also been implemented in data systems. So you don't have to write all these things from scratch, just call them. Okay, so the first thing that you can do is to calculate something called a Manhattan distance. So the Manhattan distance is simply the distance between 2 points, the straight line distance between 2 points. So if, for example, I have the coordinates or the latitude and longitude of the, let's say, the customer that is making an order, and I also have the location of, say, the company where the dispatch rider is coming from, I can calculate the distance between these two people and be able to feed that to a machine learning model to be able to predict the time of arrival. Okay, so that's the Manhattan distance. It's simply the straight line distance between 2 points. So and this is how to calculate it. If you did distance in, I think that's mathematics, calculus. The calculus of physics. Okay. Oh wow. Let me reconnect. I've not been running this notebook for a long time as well. Okay, so basically you can use this simple function to calculate that where you have the latitude and longitude of the first data set or the first feature and that of the second feature. So you can calculate that, pass in this feature. So I just define a simple function that takes. So what I'm doing is calculating the distance between the pickup latitude, and the destination latitude longitude of the riders in the sending logistic data sets. So if you come here and so you can see this is the distance, the Manhattan distance. So this can be an important feature for your model as well. There's also something called an advancing distance. So the advancing distance is a great circle distance between 2 points on a sphere, given their longitudes and latitudes. So it is very important in navigation. So if you are assuming that your riders are going to be navigating, they might have maybe shortcuts, highways, and things that they can bypass to get faster to a place. So advancing distance can help you capture most of this great circle distance between those 2 points. Okay, so the function is quite complicated and with a single distance. So please use the assist and it's stress-free. So it's very easy to do as well. So after writing this function, you just call them with the pickup altitude and longitude, destination as well, and you can calculate the great circle distance between these 2 points. Okay, finally, there is the bearing. So the bearing is the compass direction to travel from a starting point to It must be in the range of 0 to 360 degrees. So this is where domain knowledge actually comes in. So you can see we're using most of physics knowledge and the rest to create features from our logistic data sets. So we're calculating bearing. So the same method as well, but this is a formula converted to a code I can use to calculate the bearing between 2 points. So we'll do the same thing here. Also, implementing a data assist, you can use that. Okay, there's also another one called the get center point. Okay, to get the center point between two locations. Very easy. This is just simply to add them and divide by 2. So that's very easy to do. So center latitude as well. Then, so you can see that with this, you can actually get good information from your location data without having to use those GeoJSON or GeoPy services that can convert it to string of an address. Then from there start getting city names and the rest. So if you don't have the time, if you don't have the money to wait, you can use these simple functions to extract useful information from your location data. Okay, so that's where we draw the curtain for today. These are just like a tip of things that you can actually do, feature engineering tips that you can do. There are lots of other things that you can do, but I just picked some few important ones here, and we will end here for today. So I think I'll use the next maybe 5 to 10 minutes to just take some quick questions from you guys. So thank you very much. I don't know if everybody understood what I just did, but if you have any question, please, time to ask. Ernest, are you with us? Okay. Yeah, thank you. Okay. Okay, I think I'm seeing a question. Can you restate the difference between hash and label once more? Okay, for Emmanuel. Okay, so let me just quickly go there. So basically, what label encoding is doing, MC. Label encoding, when you have a large, maybe a feature with large number of classes, label encoding assigns a random integer to those classes. Let me look for it. So if I have maybe classes of food that are like 1 to 20, label encoding will randomly assign a unique integer to each of those classes. So it does not consider if there is an odd ring at all. It just assigns random integers to them. Okay, that's label encoding. And sometimes this might be bad because maybe your data set, even if they are large, has some kind of odd ring and the rest. So, but for hash encoding, hash will pass each of those categories through a function, through a hash function. Okay, so the hash function is under the rules. It just takes each category and creates a unique hash function for that category. So anytime you need to reference that category, it's just going to pass it through that function and retrieve the category for you. So the hash function is kind of like an efficient way of representing those categorical features in a low-dimensional space. So you can decide to choose maybe 2-dimension, 3-dimension, 4-dimension, instead of having maybe in one auto encoding where you have like 10 dimensions, so stuff like that. So I hope that's clear. Let me see. Okay, so please, can you quickly go through the latitude and longitude again? Okay, so what I did there was, what we are basically doing there is just trying to extract useful features from them. Okay, so we are using kind of domain knowledge as actually here. So we are calculating distance between those 2 points, say straight line distance between maybe the pickup. No, for example, each point must have a latitude and a longitude. So it comes in pair. So if I'm in say Lagos State has a latitude and a longitude pair. So that is that for that point. Then for example, somebody is in Abia State. Abia also have latitude and longitude. So what you are doing here is, for example, this Manhattan distance, you are calculating the distance between that first point, which is the pickup, and the destination point. So these functions help you to calculate the distance between those 2 points. So like I said, you should not be writing these functions over and over again. You should simply you can use data assist to do that. But if you still want to write them, they are also in this notebook, so you can copy and paste them somewhere. So this is like a straight line distance. You can read up more about them on Wikipedia. This is a straight line distance between 2 points. This is a great circle distance between 2 points. Is used in navigation. So this is the formula for doing that. The same process. Then this is the bearing, which is like the compass direction to travel. And this is like the get center point. So these are all just efficient way that you can extract information from that. So I hope that's clear. Then what do you think about just imputing missing to categorical features rather than using the modes? Imputing missing. I don't get what you mean by imputing missing. Do you mean by using the imputer function?
Hello, Rising.
Yeah, I can hear you.
Hello, Rising. Okay, so
you.
I would like to explain what I meant.
Okay.
Oh, what I mean is, what do you think about just creating another label, another level, and just indicating that okay, this NaN is missing rather than just using the mode.
Oh yeah. So
that's what I mean. Then number two. Okay. Should I continue?
I think I should just answer that before you continue.
Okay, thank you.
So the thing is that yes, most people do that. So they kind of feel and still indicate that this particular feature is missing. So you can do both, but I think feeling will give you more. How will I put it? It will give you a more robust feature than just indicating. So what you can do is to do both. Our advice is to do both. Feel with a particular strategy, then also you can create an extra column to indicate which of them are missing. So it's like giving your model an extra edge for that particular feature. Okay, then your second question was filling numerical features with a -999. Okay, so most people or most database or data engineers normally fill missing value with random numbers like 999, 98, 96, and the rest. So it's the same thing. Those features, you still have to fill them when you are working with them. So you should not work with these values like that, this -999. It's just a method of indicating that this particular instance is missing. So it's like using none as well or null. So you still have to fill those features.
Oh,
you don't have
to
then. Work with them like this. Yeah, they're just telling you that okay, these features are missing, so just put -999.
Okay, so I'm not even supposed to feed it into the model using -999.
No, if you feed it into a model, you are trying to deceive the model. You are trying to tell the model that we're expecting values like this -999 from the user as well.
Oh, okay. Yeah. Thank you for this.
Then, can you tell us what frequency encoding is and when to use them? Yeah, so frequency encoding is also another type of encoding scheme, almost similar to target encoding. They are kind of newer scheme. So I think what they do is in the high level, what they do is that they count the frequency of the class in respect to the output. So they kind of consider both the target as well. So you count the popularity, that how many times does the class appear. And I think I've not used it for a long time, but I think it's maybe calculates the mean of the total number of times it appears, something like that. I'm not really familiar with that frequency encoding, but I think I've used it just once. But it's something you can actually read up on, and which is also what I'm going to do as well. So the frequency encoding can also be used when you can use it, maybe for example, instead of using target encoding, you can actually try it. But one thing I would like to mention is that most of these encoding schemes, they don't really work well. Yeah, so to say, they don't really work well like that more than the traditional methods. So most of these guys that do maybe cargo competitions and the rest, they actually use most of this kind of encoding scheme. But I found out that, I don't know, most of my work that I do, found out that most of this newer encoding scheme kind of overfits more than the older types. But like I said, it's experimental, so you can also try it as well. Then the next question, when you created the interest elapsed, do you drop the features used to calculate the new feature? No, you don't. Don't drop the features. You are just creating extra features to make your model be able to do better. So you don't drop the features, the other features. Yeah, so
thank you very much.
Right, sorry. So my question is on the rescaling of features. Can you kindly brush through? So the rescaling is just trying to take the range of your features and compress them, bring them down to a lower level. Okay, so if I have features that I in, say, maybe income of a person can be 50,000, 100,000, and the rest. So the lowest feature or the lowest amount in that particular feature might be say 10,000. So you can see the range is very high. But if I have another feature that can be say ratings, for example, and ratings can run between 1 and 5. So you can see the scale are different. So training a model on this kind of features without rescaling them can result in slower training, can even make, if you are working with neural networks, can lead to weight exploding and stuff like that. So the rescaling are just techniques that you use to bring down these features to the same scale. So if you apply a standard scalar or reverse scalar to your feature that is in 10,000 scale, it can bring it down between 0 and 1. If you apply it to the ratings with 1 to 5 scale, it can also bring it down to between 0 and 1, so that all your features are in that same scale and your model can work better. So the second question was also after engineering new features, do we drop the feature that lead to the so I just explained that. Yeah, you don't do that. Except say for example you are how will I put it? No, you don't do that because you are trying to create new features that will make your model improve or be better. So you don't drop the old feature, you still leave them the same.
Hello, Rising. Hello, Rising.
Yeah?
Please, can I create this scenario? For
Okay.
instance, now, when we are talking about health data,
Okay.
we know that we can actually use the weight and the height of an instance to actually generate a new feature called BMI, the body mass index. Now, so if I have the height and the weight, and I decide to kind of like calculate the BMI from these two features, do I still need to keep the height and weight
Yes,
as a
you
feature
should.
that I need to
Yes, you
feed
should.
into the model? Okay.
Yes, you should, because the BMI might not capture the relationship between your height and weight to other features. Because your weight and your height might be correlated to other features that helps your model do better. So if you remove them, BMI on its own might not be able to kind of embody those two features on its own.
Okay. So
So you
how
should
do we
keep
now
it.
know when to know that okay, we are not adding more than is necessary to the
Okay,
number,
so
like increasing the dimensionality of
okay,
our
so
features?
that is when the experiment comes in. So that's why you have to try it, check your performance, see that it is not overfitting. If it is overfitting, that's when you must start removing some features or doing some other things. So that's why it's experimental. But from the start, you should not drop features. Most of the time, what most people do is to train with all their features at once first before they start removing features. So because you can't tell which features might be important from the start. So you just have to post it all in. Sorry about that. Okay, sorry about that. You just have to put it all in first and try it. Uh, so let me see which other question was there. Please elaborate on how we can use heat map to extract features and correlate in particular feature. So the heat map is just a plot. It's just a plot in SNS, a plot type in Seaborn. Here was that. Okay, so what you do is, first of all, you calculate the correlation of a data set. So this sandy data set, if you do the dot core, it's a pandas data frame. So you can call dot core on it. So this is just like calculating the correlation with data frame. So it's going to return a matrix. So I don't know, let me see. Let me run. Maybe so that you can see it. Run before, yeah. So I'm going to create a cell and go on this. You can see it's going to create a correlation between all the features and themselves. This is a correlation matrix. So whereby you have platform type. So you can see this is the correlation value 1.0, meaning highly correlated. Why? Of course, a feature must be highly correlated to itself. Then you have placement day of the month and platform type. Look at the correlation, it's close to 0, meaning it is not so correlated. So meaning 0, close to 0, not so correlated, close to 1, highly correlated. So what heatmap is doing is just taking this matrix, this giant matrix, and plotting it for you. So you can see platform type on top. This with itself, highly correlated, white. So you can see all the diagonals are white. Why? Because every feature is, first of all, highly correlated to itself. So, but if you look at other features, like for example, this, where you have distance and time from pickup to arrival, it is okay over 0.5 also. So you can see that distance is correlated to the target, which is time for pickup to arrival. So if you are working on this model, you will know that distance is a very important feature to predict time of arrival. And obviously it is, because if the distance is far, normally the time it will take a longer time to get there. So you might not know that, you might not decide to create new features from this distance because you are trying to write on the fact that it is highly correlated to the target. So this kind of correlation plot is very important. You can also see temperature and platform type. There's a kind of small correlation. I don't know what kind of correlation is that, but so you can investigate that. Another question: how do I know which operation to cross? Which operation the to cross is actually doing? Yeah, so I think you can specify that. Yeah, let me see. Polynomial. By default, it's supposed to be a multiplicative. Let me see. Numerical features. Sorry, let me run this cell first. Dog. I have to find my dog. Okay. So generate a new feature matrix consisting of all polynomial combination of the features with degree less than or equal to this. For example, if a sample, okay. So what it's doing is actually creating a degree polynomial. So not necessarily multiplication and the rest. So the first thing to do, a raised to power 2, a times b, b raised to power 2. So if you are crossing a and b together, this is what it's going to create for you. Going to first of all create the single column which we have already, a and b which we have already. Then it's going to do a raised to power of 2. So it's, how would I put it, raising a to itself. Then it's going to multiply a and b together. It's going to do b raised to power 2. So these are the features it's going to create from just this. So it's not necessarily multiplying them, adding them together. These are what it's going to be doing on those particular data sets. So you can specify the degree as well. So if you specify 2, the highest power will be 2 here. But if you specify 3, as you want to create degree 3 polynomial, so it's going to do b raised to power 3 as well as a raised to power 3, and that. So that's for that. Yeah, no. How best can one work with ordinal data? Is it necessary to convert them like categorical data, or we can just use them like that? By ordinal data, I mean something like a scale of 1 to 10, with 1 indicating very bad and 10 very good. So it's already in numerical form. So if you have data like this, it's already in numerical form, so you can just work with it like that. It's already in the best format possible. But if it is not in numerical form, you have to maybe convert to integer or float type. I came a little late, so I don't know if you already touched it, but I would like you to recap in case you already mentioned it. Okay, I've done that. Then if two features are highly correlated with each other, is it advisable to drop one of them? Yeah, so the thing is that, yeah, most of the time, if you have two highly correlated features in your data set and you're trying to predict a target, most of the time it's advisable to drop it because they might interfere with each other. So, but like I said earlier, you still have to do an experiment. So you can try to use the two to model and see if it performs well. If it performs well, you can leave it, but if it doesn't, you can remove it as well. But most of the time, you have to remove it. Also, is it possible that too many correlated features can cause overfitting? Yeah, definitely. Too many correlated features can cause overfitting in machine learning models. Okay, so I'll stop sharing now. Thank you, everyone. I hope I was able to. Oh, yes, I question. Okay, so Nelson said, apart from dropping one feature from two correlated features, is there any other information of change that we could derive from that information? Yeah, you can try combining them together. Maybe you can try adding them, maybe, or crossing them together and taking that single feature, then maybe removing the two. So you can say if I have two features that are correlated to each other, I can decide to create a product or create a joint product from the two of them. Then I remove the two and use just that single feature. So what I'm trying to do is essentially I'm capturing the information in those two correlated features into a single feature. So it might work. But like I said, and I will always say, you have to do the experiment yourself. Okay. 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 Yeah. Okay. Okay. So PCA is basically dimensionality reduction technique. So there are lots of techniques like that, but PCA is very popular. So what you basically do is take your high dimensional vectors or your high dimensional data. Say when I mean high dimension, something like say maybe I have 10,000 rows and maybe 100 features. Okay, because even just recently I worked with a data that had over 700 features. So imagine you have 700 features in your data set. So to work with things like that, what you can do, PCA can help you take this high dimensional data and project it into a smaller or a lower dimensional data. So if I have 700, I can use PCA to project it into say 3 dimension or 4 dimension. So most of the time, if you have this kind of large dimensions, your model can seriously or massively overfit. So it is best to use this kind of algorithms like PCA to kind of compress or reduce the dimension of the data before you pass it to your machine learning model. So there are advantages. That's the advantage, but there are disadvantages as well. Disadvantage in the sense that it becomes practically uninterpretable because if you convert say 100 dimensions to 3 dimensions, you are doing lots of compression and many informations are going to be lost. So because okay, 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 definitely. Yeah, that's it. Definitely, definitely you can do that. So it will help to reduce the dimension. Maybe you can take from that 10 to like 3, then you pass just those 3 to your model. Okay. So yeah. All right.
Please, can I ask this one last question, please?
Okay. Okay.
Please. Okay, so Ryzen, after doing all of this feature engineering, and we want to actually we've done our modeling to we want to take it into production. Is it
Okay.
through the process of automation that new model will be able to get information from new data sets and automatically kind of like engineer the features? Do you understand what I'm trying to say?
Yeah.
Like,
Okay. So
we had to do this by hand ourselves
yeah.
through
Yeah.
our own domain knowledge. How will our the model we have created or built, be able to recognize that, okay, this new data set that is coming in is not coming in form of features that have been engineered? So is
Okay.
there a process of automation or something that goes along when we are trying to kind of like put our model, deploy and all of that?
Yeah. So basically, what we are doing is during the process of experimentation, you are kind of getting an understanding of the process of how your data comes in the raw format. What are the steps that you take to transform it from that raw format to a ready-made data set? So you are kind of designing a pipeline during your experimental stage. So, for example, data comes to raw format, you use a function to fill missing values, use another function to encode, use another function to standardize. So these 3 different functions are part of your pipeline. So what you do is that you take this pipeline, you rewrite it. For example, you can take your notebook and you write it as a script, for example. So you rewrite these functions in a standard way so that once you get your new data, it's going to first of all pass through these pipelines before it gets to your model. So you don't just take a raw data and pass it straight to your model. No, it's going to follow the same process that your training data followed before it to get to the model. So you, for example, you write those 3 different functions in your pipeline. So once your test data comes, it passes through the first function, which will fill missing values using the same strategy you use in your training data to move to the next stage, which is say encoding, which is using the same encoding scheme your training data used. Then moves to the next one, which is standardization. So it follows the same pattern before it gets to your model. So whatever you are doing in experimentation stage, you have to like rewrite them into a pipeline that each new data must follow. So that's how you take that from experimentation to production. I don't know if that's clear.
Thank you so much. Very
Uh,
clear. Thank you so much.
uh,
Thank you.
all right. So in the absence of any other question, I'm very, very hungry. I need to go and eat. Yeah, thank you all for listening. I really appreciate it. Thank you all for listening.
Thank you.
Yeah, it's not a graduate. It's not a big goal.
Ernest, we appreciate you too. Thank you for always leading us. All right. Today is a very good class, a very educative
Thank
class. I
you.
learned so much and I'm better for it. Thank you.
Thank
Thank
you.
you so much.
Thank you, Ernest. Thank you very much. This was a wonderful one. Madam Yinka, good to see your face.
Hello, sir. Good afternoon,
Good
sir.
to see your face, madam.